Welcome everybody to this video for Algebra 2 Unit 9. In a moment you'll actually see a video I made a few years ago before we switched curriculums this year. During this switch, we decided to keep most of this unit for probability and statistics, but renumbered this unit and a lot of the sections in it. And we also decided to slightly change the layout of things as we did it to make it more similar to the rest of this new curriculum. And because of that, you're actually going to notice that during this video, some of the formatting and layout of things is going to be different than the formatting and layouting of things in your notes, once again compared to the video you're about to watch. But with all that said, the definitions and examples will be the exact same and in the same order and everything, all the same numbers, same wording of everything in both the video and your notes that you have in front of you. So don't worry about that. I just wanted to give you a heads up so that way you weren't caught off guard or anything and that you thought you weren't watching the wrong video and getting the wrong notes. And with that, enjoy the notes.
Welcome everybody to Algebra 2, Section 9.2, Sampling, Methods, and Making Predictions. So, goal of sampling is to obtain a representative sample because the statistic is obtained from the sample is a good estimator of the population. So essentially you're saying, hey, what's going on with a few of the people, and then expanding that out saying, okay, what does this look like going on with everyone then? So some sampling methods can result in biased samples though. And those might not be representative of the population, and those can produce statistics that lead to inaccurate conclusions about the population. And so the key is to make sure the sampling is random and that it's very big. So you want as many individuals in the sample as possible. So for example, you could say like, if you were sampling school lunch and saying what students like for lunch. And let's say you just sample freshman boys. Well, freshman boys might have a very different view on what they would like for school lunch compared to seniors, for example, of any gender. And so pulling data from the freshman boys only could give a very biased result if you say, well, this is true for everyone because it was true for these freshman boys. So rather than sticking with one group, you want to make sure it's random, so it's going across groups, and it's big, so you're getting a lot of different people. So here we have 5 different sampling methods. The first one is simple random, and it's just each individual in the population has an equal chance of being selected. So it's essentially like you're drawing names out of a hat almost. Self-selected example, individuals volunteer to be part of it. So the individuals are selecting themselves. Convenient sample, you just select based upon how accessible they are. So like, oh, the people in the classroom right now. All right, that's convenient for someone. Systematic sample, so members of the sample are chosen according to a rule, such as every nth individual in the population. So you're saying maybe every 3rd person that walks into a movie theater. And stratified, which means that it's divided, the population is divided into groups, and then individuals from each group are selected. And then typically it's through random sampling within each group. So let's say you're going to take 10 freshmen, 10 sophomores, 10 juniors, 10 seniors. That would be an example of stratified. So here, in each of these first 2 examples, we're going to identify the population, classify the sampling methods, and then decide whether it could result in a biased sample, and explain that. So example 1 here for A, B, and C, the officials of the NFL want to know how the players feel about some proposed changes to rules. So they decided to ask a sample of 100 players. So the population that we're talking about here are who we're trying to survey. And so we're trying to survey the players in the NFL. And you might say, NFL players, something like that. Different way of phrasing the same exact thing. So the first way they could choose them, or talking about them choosing them, is they choose the first 100 players who volunteer. So 100 players volunteer, and they say, great, you're the first 100, we'll take you. So this is a self-selected example, or self-selected sample, because it was those that volunteered first. They chose to be in it. And then, do we think this might be biased? Well, yes and no. I would say overall, yeah, there's a good chance it could be biased. We don't know if it will be, but definitely could be biased. And the reason why it could be biased is because maybe not every player cares about the rules as much as another player, but those that care more about the rules, so those that care maybe heavily about the rules, are more likely to volunteer. So if somebody doesn't care about the rules, they might have a different viewpoint on the rules if they were asked. But if they're just saying, well, do you want to answer? If they don't care, they're going to say no more than likely. Example B, the officials randomly choose 3 or 4 players from each of the 32 teams in the NFL. So this would be a stratified sample. So it's from each team will have a pretty equal representation, whether it's 3 or 4. And then within that team, within each team, it'll be done randomly. So that would be our definition of stratified. And then this one is not likely to be biased. It's still technically possible, but it's random enough, and then you have a big enough different group with each different team that it's just not likely to be biased. If it would be biased, then that's just pure luck that it would happen to be biased. So it's not likely to be biased since it's random. The biggest thing is that it's random. And then the other factor is that each team is represented. The reason that second part is important is because some teams might be more prone to playing a certain style compared to another team. And so some teams are potentially would have a more biased opinion compared to rules that would favor one style versus inhibit or detract from a certain style. C, the officials have a computer randomly generate a list of 100 players from a database of all NFL players. So this would be our simple random. So it's like they were drawn out of a hat. In this case, it's just drawn from a computer. And this one's not likely to be biased either. And it's because it's random. And once again, that's going to be the biggest deal in whether or not something's likely to be biased or not, is whether it was truly random or not. Example 2. Administrators at your school want to know if students think that more vegetarian items should be added to the lunch menu. So, whose population? Well, students at the school. So let's say the administrators survey every 25th student who enters the cafeteria. So this is a systematic example, or systematic sample, I should say. And this one's not likely to be biased. Once again, it's still possible. But it's because it's random, again, and a wide range of students will be surveyed. Now let's say the administrators survey the first 50 people who get in the lunch line to buy lunch. So this is what we would call a convenience sample. So the only reason they're picked is because they were there. Now, it's not guaranteed, but this definitely has more of a potential to be biased, so I would say it's likely to be biased even. And there's a few reasons. Um, One could be it doesn't include students who don't buy lunch, you know. So one reason is, it doesn't include students who don't buy lunch, like I said, because maybe they would start buying lunch if there were more vegetarian options. Maybe you can think of other potential reasons of why this is, could be biased as well. Um, Maybe, the first 50 students are all in one friend group and they all have similar dietary restrictions or preferences. And so that could skew it one way or another as well, just taking the first 50 like that. And then the administrators use a randomly generated list of 50 students from a master list of all students. So this is, once again, simple random. And this one is not likely to be biased at all. Not impossible, but it's just not likely. And that's because it's truly random. All right, on the next page here. So some different thing we're doing now, or something different we're doing now. So making predictions from a random sample. So data can be numerical, such as heights or wages, they're numbers, or categorical, such as eye color or favorite food. So like, you don't have a number associated with your eye color. You would say, oh, it's like brown or blue, for example. Now, while a statistic like mean is appropriate for numerical data, it's not appropriate for categorical. So that would be proportion is what's going to be better for us there. And that's the relative frequency of the category. So it's basically how often it appears compared to the total number of people we have. So it's like how many people prefer soup over salad at a restaurant. Example 3 here. So a community health center surveyed a small random sample of adults in the community about their exercise habits. So of the 25 people surveyed, 10 said they exercise regularly. And the table lists the data for those 10 people who said they exercise regularly. So don't forget there's 15 people not included in this table as well. So we're supposed to calculate statistics from the sample and use the statistics to make predictions about the habits of the approximately 5,000 adults living in the community. So a very small sample, and we're trying to spread it out over the larger population. So here we can see that this first individual prefers running, and they spend 30 minutes running 4 times a week. Whereas this next individual prefers walking 20 minutes for 5 times a week, and you can just go on and so forth. So calculate the proportion of adults who get regular cardio exercise and the proportion of runners among those who get regular cardio exercise. Let's pause there before I go to the last part of it. So proportion of adults who get regular cardio exercise. So it said 10 people out of those 25 were the ones who said they get regular exercise. So that would mean that 10 out of 25 is 0.4, aka 40% of people, 2 out of every 5 people. So then we're supposed to say, okay, now out of those, how many would prefer running out of those, okay? So out of the 10, so the 10 we have on the table, we say, okay, so the running, how many prefer running specifically? Out of the 10, we have 1, 2, 3, 4, 5 of them prefer. So that would be 1/2, aka 0.5, or 50% prefer to run of those that exercise regularly. So now we're supposed to use the proportion to predict the number of runners among all adults living in the community. So if you have 5,000 total adults, well, we first have to narrow it down before saying, well, 50% of those run. No, not true. only 40% of those exercise regularly. So we'd have to first multiply by 0.4, or 40%. It's the same thing, because 40% of the 5,000 exercise regularly. So that gives us 2,000 that exercise regularly. Also, I don't know why I abbreviated exercise EXC earlier. And then now, of those 2,000 that exercise regularly, half of them, or 50% of them, 0.50 or just 0.5, are runners. So it would be 1,000 people that would run regularly. And that's if this sample of 25 adults holds true for everyone. So it's very possible that in this group of 25, because it's so small, that you had a disproportionate amount of runners. Maybe there's too many or too few. So the real number of runners out of the community might be more or less than 1,000. But we're just using this to predict how many there might be. I want to note that an additional way you could have done it mathematically is saying, hey, if 5 people from the survey said they prefer running, that means that's 5 out of the 25 total people surveyed, which is the same thing as 0.2 or 2% or 20%. So you could have just done 5,000 times 20% or 0.2 right away and get 1,000 as well. The same thing, the same result would be the case, or would be attained, I should say. On letter B, we're supposed to calculate the mean duration of exercise for those who get regular cardio exercise and the mean frequency for those who get regular cardio exercise. So we're saying of the 10 in the table, what's the average duration of their exercise? So we find the mean of all these numbers by adding them up and dividing by 10. And the mean duration is 48 minutes. And then if we find the mean frequency for how often they work out, so you add all these up and divide once again by 10, then you would end up getting 3.7 times per week on average. You would not want to round that there. Because you round that up to 4, that's going to skew our results. Now we're supposed to use these means to predict those who get regular exercise, how many hours they spend doing that a week. So we're saying, okay, of the 10 out of 25, of the 40% that exercise regularly, how many hours are they doing that a week now? So we say, we'll take 48 minutes times 3.7 times per week. So each time would be about, on average, 48 minutes, and if they're doing on average 3.7 times a week, that gives us 177.6 minutes per week. So now our question was asking for not minutes per week, but hours spent per week. So in order to go from minutes to hours, you divide by 60, and you get 2.96 hours per week, which we're going to say, rounding wise, that's about 3 hours per week. And we're more okay with rounding there at the end because we're saying it as a result after we did a lot more math. So you don't want to round early here at 4 because you're still manipulating those numbers by multiplying and dividing. And the earlier you round, the more it's going to throw it off. Whereas at the end, it can be a little more acceptable to round. If you would have left your answer at 2.96 hours per week, that would have been great. So we're saying on average, those people who exercise regularly exercise 3 hours per week. Now, obviously, some are going to exercise more or less per week than others. So how much confidence do you have in the predictions made from the results of the survey? And explain your reasoning. So personally, I would say that the sample was random, so that's great. As I said earlier, that it was done randomly. So which is good. However, it may be too small. I was kind of talking about that earlier as well. And the reason it might be too small is you might not be able to know if the predictions will be accurate. So the more and more people you include in your sample, the larger it gets, the more likely it is you'll have accurate results and accurate predictions. All right, let's talk about observational study versus experiment. So in an observational study, research determine whether an existing condition, called a factor, in a population is related to the characteristic of interest. For instance, an observational study might be used to find how frequently people that smoke suffer from heart disease. So in the study, being a smoker is a factor, and having heart disease is a characteristic of interest. So that's what they're really tracking is the heart disease, and they're seeing, does smoking change it? Is that a factor in it? So in an experiment, however, researchers create a condition by using a treatment on some of the subjects. For instance, an experiment might be conducted by having some people with eczema take a vitamin E pill daily and then observing whether the symptoms improve. So in the experiment, taking the vitamin E pill is the treatment, and the improvement of the symptoms is the characteristic of interest. So what are you most curious about, and then what is changing here? So usually an experiment is best because you can see how one variable affects another, but it's not always ethical to complete an experiment. For instance, you can't ask people to smoke to see how it affects their health, so you would only be able to do a study. But if you can do an experiment, you can get a better idea on if it's changing it or not, because you get to control more of the factors and just narrow it down to one factor that's changing. So example 4, on ABC, we're going to determine whether these are a research study or whether the research is an observational study or experiment. And if it's an observational study, we're going to identify the factor, and then if it's a treatment, we're going to identify or if it's an experiment, we're going to identify the treatment. And we're also going to identify the characteristic of interest regardless of which one it is. So on A, researchers measure the cholesterol of 50 subjects who report that they eat fish regularly and 50 subjects who report that they do not eat fish regularly. So write down whether or not you think this is an observational study or an experiment. All right, well, this would be an observational study. I'm just going to abbreviate because I'm lazy. And the reason why is because they're not changing anything on anybody. They're just seeing what happens. They're only observing. So the factor is whether or not they eat fish regularly. That's the change, that's the difference between them. The characteristic of interest, so what we're curious about to see if it affects anything, is the cholesterol levels. Letter B, go and try it. So if they have 100 subjects with high cholesterol and they are having them take fish oil pills daily for 2 months, and they're going to monitor the cholesterol. So this would be an experiment because they're actually changing something. They're altering it. And so rather than a factor, you have a treatment. And the treatment is the fish oil pills. And specifically in this case, daily for 2 months. And once again, we have a characteristic of interest. And so we're saying, what are we most concerned about to see if this, of what's changing or not? And we're curious once again about the cholesterol, specifically the cholesterol level, if you want. Researchers monitor the driving habits of 80 subjects in their 20s and 80 in their 50s for 1 month by using a GPS device that tracks location and speed. So write down what you think this one is. This one is an observational study. Nothing is being altered between the two. They're merely just observing what's happening. So the factor here that they're seeing the difference between these groups that they set apart is a person's age. So whether a person is in their 20s or their 50s. And the characteristic of interest, what they're curious about, is their driving habits. Sorry, I had a yawn there. So they're saying, do we have different driving habits based upon their ages? Now I want to note here that be careful that just because two things are correlated does not mean that one causes another. So just because as something increases, another thing increases or decreases, doesn't mean that they're related. So we didn't talk about this in 2023 school year because we didn't have those graphing calculators in on time. And that's this part right here. Otherwise, as you know, from unit 1 in your calculator, we can talk about how linear regression and whether or not something has a strong correlation, whether or not they look to be related. Now, these three data sets have nothing to do with each other, but they look to be very heavily correlated. So this first one is quite humorous to me, is the global average temperature, and you can see it going up over the course of the last couple hundred years there, and the number of pirates. Well, you can see the number of pirates is going down, so temperature is going up. That doesn't mean that because we have less pirates now, it's warmer. Not by any means. Although that would be quite funny. Here you can see the number of individuals diagnosed with autism going up in the purple triangles, and as it also goes up, we can see the organic food sales increasing over that same time frame. And this is not saying that increasing in organic food sales is causing autism in any way, because there is no relation there, at least that we know of, I should say. And then this last one is also kind of humorous to me, how silly they are to be thinking they might be related to each other, even though it's a sad thing like highway fatalities. So we can see highway fatalities going down over the course of years as we're importing more and more lemons from Mexico. So someone might look at this graph and say, well, clearly, the more lemons we get from Mexico, the less, fatalities we have on the highway. So we just need to keep importing more and more lemons and we'll be fine. That's kind of a silly thought, just because they would have nothing to do with each other at all, even though we do see those both changing in similar ways over time, one going up and one going down. All right, that is it for section 9.2 today.